Yay. We're here and I'm responding. It's exciting, isn't it? So we are talking about the final discussion on the more theoretical aspects of boundary layers. And where we have sort of skipped over a little bit was flow separation. And in the process of discussing flow separation, it's really something that's caused by a boundary layer moving against increasing pressure, and it's the adverse pressure gradient. So we have two types of gradients that we consider. The adverse and the unfavorable gradient, which is dP dx, is greater than 0, which means you have increasing pressure as you move downstream. Or favorable, where you have decreasing pressure. And increasing pressure is associated with velocity decreases. It often occurs on the rear of a body and can lead to flow separation. And you know, a perfectly good example of that are any of the very large cargo trucks that you see on the 401, because they're designed to look like giant rectangles, and there's flow separation associated with it. And in fact, I was reminded of this because if you go over the Burlington Bridge during these windstorms that they've been sort of telling us about, I would not want to be in one of those trucks because you have a lot of flow separation and a risk of overturning. Favorable pressure gradients, pressure decreases, velocity increases, occurs on the front of the body, and separation does not occur. And you'll see this when we start to look at nozzles and various other types of flows. Pressure gradient affects the shape, and I'll go into more detail about this in a minute. But I have wall shear stress that goes as mu del squared u del y squared, so the Newtonian stress, and is equal to dP dx. For a favorable case, that stress is going to be a positive or negative value, and in that case, negative curvature, rounded, stable profile. If you have zero curvature, flat plate, and positive curvature, S-shaped profile with an inflection point, which leads into this, which is the same figure that I showed on the previous slide, but here's the favorable pressure gradient, and you'll notice that it's nicely sort of filled out. It goes to 0 at the wall, and nothing really is happening. There's a bit more, it's a less steep curve than in the case of the 0 gradient, which is no separation. Still, everything is sort of attached to the wall. Nothing is happening to it. On the other hand, in the right-hand set of figures, you have 3 different types of cases, and the first one is the weak, so pi is point of inflection. Du dx is less than 0, and del p del x, or dP dx, is greater than 0. And you'll notice at that point, you still have there we go. There we go. Sorry. So you'll notice at that point, in the weak case, you still have a point that is attached to the wall. There is no reversing flow in that case, but it's sort of, it's not quite at the edge. On the other hand, when you get to a critical adverse pressure gradient, there's no way to maintain the flow without having a reversing flow in there. And if you increase the disturbance, increase the wall shear stress by a little bit, you then see an excess of pressure gradient, and that's separation. And that's a separation where you have a reversing flow that appears. Weird. Separation occurs where the wall shear stress is 0. So we have roughly 70, 80 years of measurements trying to measure a good wall shear stress. And it's really hard to do that. And so a lot of the literature you might see in fluid mechanics is going to look at how to define that. And so primarily it was looking at things like backward-facing steps. And a backward-facing step is a standard So a backward-facing step is just this. You have flow coming in left to right. Flow goes over, and you have a recirculation that will appear. That recirculation is going to be constant, but there's going to be a point where shear at the wall is equal to 0, and that indicates the difference between when flow is moving forward and when flow is moving backwards. And so we use that as an indicator. And I just want to see why. I know why. Indicator of what's happening. So if you're looking at nozzles, and you've looked at nozzles already, you're aware that as you come in, you have an nearly inviscid core flow that's there. That's the center region that's not affected by the walls. You have decreasing pressure as you bring the area down. You have increasing velocity. And this is where you start to tie back to your Bernoulli equation. And you have a favorable gradient. At the throat, you have constant pressure and area, so it doesn't change. And so in those cases, you have a constant velocity and 0 gradient. And then finally, you have a diffuser. As you come out, you have increasing pressure and area, decreasing velocity, and an adverse gradient. And here is where you see this sort of separation. And we don't talk about dividing streamlines or anything like that in the course. I think I've done a couple cases where I've talked about them, but basically they sort of describe, just 2 seconds. They just basically describe divisions in the flow. Go ahead. Is separation? So if it's one of those things you kind of look at and you say, yes, I know what it is. The definition of it is where the wall shear stress goes to 0. So it's going to be where you see a flip over in the sign of shear stress. So generally, we can't measure 0. We can never measure 0, but we can measure plus minus. And so we tend to look for a region where, on average, that separation occurs. However, when I look at it in a flow, I'm going to look at the flow and say, hey, that looks like a recirculation zone, and that's where I'm seeing this sort of circulation in the flow. Yeah. So that's 2 ways to approach it, but generally, wall shear stress of 0 is the important criteria. So you have 3 sort of different cases. You have the nozzle, favorable pressure gradient, throat, the 0 gradient, and finally the diffuser, where you have a adverse pressure gradient. Flow decelerates, boundary layer thickens. If the diffuser angle is too large, flow separates, causing significant losses. And we talked about that in chapter 6. We looked at various diffusers and tried to figure out what the angles are and how they affect the flow. We have Kármán's momentum integral. So we have Kármán's momentum integral, and we end up with this equation right here. And I'm not deriving any of these relations. I'm not going, and in fact, I'll do a couple examples where I say, here's an exact solution. I'm not going to discuss really how they came about. I will discuss how we apply them. And so generally what you're doing in this chapter is recognizing what the relationships are and using those relationships, not necessarily rederiving them. So here I have shear at the wall over rho u squared, which you kind of recognize right away as a friction coefficient. So it's half of the friction coefficient. And if you do that, you can set it up in terms of d theta dx, h plus 2 theta over u du dx. Now, theta is the boundary layer momentum thickness, and I think, I know I did update my slides for this for last time, so we had a set of definitions for that, but basically it's how much momentum is taken from the flow because of the existence of the boundary layer. Delta star is the displacement thickness, which is how far you would have to displace this flow because of the boundary layer in order to have an equivalent frictionless flow. And so if you define h is equal to delta star over theta, that becomes something called a shape factor. And du dx, again, rate of change of free stream velocity, and it's related to the pressure gradient by Bernoulli's. dp dx is rho u du dx. And this is how we analyze boundary layers. So again, not a real discussion in terms of how to do that, but just sort of saying, hey, we do have these relationships. We made a whole bunch of simplifications. But in the process of doing that, we have laminar flows and turbulent flows. So the laminar and the turbulent flows are there, and you can see that you go from a favorable pressure gradient to a certain value, and in the laminar case, it becomes 3.5 for that h. So you're looking at the blue lines are h's. Y over delta is the distance along the boundary layer, and u over u infinity on the x or y-axis, excuse me. On the right axis, and again, you recognize that turbulent and laminar flows, laminar boundary layers and turbulent boundary layers, look very different. It goes for a flat plate with a favorable pressure gradient at the top, and then separation at the bottom, but the value is 2.4. So this becomes a really useful value, this ratio between displacement thickness and momentum thickness, in order to indicate sort of a threshold of separation. And I mentioned earlier that measuring shear stress at the wall is very hard to do. It's not so hard to calculate those two terms. And so you have an idea of when exactly along a flat plate that might occur. And this is, again, it's kind of empirical in terms of how they do it. They sort of do a little bit of hand waving in the Navier-Stokes equation. Then they apply some of the empirical results from experiments, and then they come up with this. So that works really well. Thwaite introduced another approach, and it's a method of analyzing laminar boundary layers. So again, we're kind of limited to doing stuff with laminar boundary layers with pressure gradients, and we try our best to sort of extend it as much as we can, but there, again, not much we can do. Thwaites proposed boundary layer properties using a single dimensionless parameter, and again, I kind of want to tie back to chapter 5. It's really kind of neat that you can do all of these types of analyses with relatively simple tools. So momentum thickness squared over kinematic viscosity times the velocity gradient du dx. And again, something you can do at home, just check and see if that is in fact dimensionless. And what it does, again, you are not deriving this. You are expected to be familiar with it and sort of recognize it, but that's it. So Thwaites' integral formula, theta squared is approximately equal to 0.45 kinematic viscosity over u to the 6 x integrated 0 to x u to the 5th x prime dx prime. And the important thing here is lambda separation is equal to minus 0.09. That's, again, empirical. You're not expected to solve these or derive them from first principles. You will benefit from knowing that they exist and keeping them in the back of your head. So we could consider I had an example. So we have a Haworth velocity distribution. So u is a function, or is equal to u naught 1 minus x over L, and it represents an adverse pressure, a constant adverse pressure gradient. Compute using Thwaites method x separation over L, and compare to the exact solution of 0.119863. And again, this exercise is only there to convince you that you can do these sorts of things pretty well. So if you have u of x, you have du dx, which is minus u naught over L. Just do the differentiation. And theta squared is equal to 0.45 nu over u naught to the 6th, 1 minus x over L to the 6th, 0 to x, u naught to the 5th, 1 minus x prime over L to the 5th, dx prime. So I'm going to set a couple things. T is equal to x prime over L, and dx prime is equal to L dt. That's a constant. U naught to the 5th, 1 minus x prime over L to the 5th, integrated 0 to x, dx prime equals u naught to the 5th times L over L plus t to the 5th dt, u naught to the 5th L. Ugh. And you can solve through and you get u naught to the 5th, L over 6 times the quantity 1 minus x over L to the 6th for those integral bounds. Combining all the terms together, you get this. So all you're doing is you're just sort of multiplying everything together, dividing it out, combining terms. It's a lot of the mechanics that you have to go through, but it's not that bad. So I have theta squared. So from theta squared, I can say lambda is equal to theta squared over nu du dx, which equals 0.075 nu L u naught 1 minus x over L 6. And that quantity multiplied by that du dx that we calculated at the very beginning of this example. All right, so we have all of that. Everything's there. We can then combine everything. And lambda is equal to minus 0.075, 1. minus, there we go. 1 minus x over L to the minus 6 minus 1, and there. Okay. I don't know what my pen is doing. So you have a value for lambda, which is that parameter that we're interested in looking for in terms of separation. So if we know that lambda is equal to negative 0.09, so we can say 1 minus x separation over L to the minus 6 minus 1 0.075 negative equals negative 0.009. That will I'm skipping a few steps in here, but basically just getting to the point where I have a relationship between x separation and all of the constants I have in this expression. If I do that, I divide out the 0.075, add the 1 to the right-hand side, I end up with 1 over 2.2 or 1.2. Just a second. That was supposed to be 2.2. So if I find the separation point, that's going to equal 1 minus x separation over L equals 1 over 2.2 to the 1/6, which is approximately equal to 0.877. X separation over L is equal to 0.123, which is a really good value. It's very close to the solution, which was 0.11983, whatever it was. Go ahead. Yeah, I kind of rushed through this right here. So basically what I'm trying to do is I'm trying to make this, take this equation, separate it out into the parts I want to solve. So here, for example, I solved the integral equation, found theta star, broke it down first of all in terms of that first integral, then the next step. The only thing that I needed to do once I had that solution for lambda was say, hey, separation occurs at negative 0.9, and then equate that to the solution I had for the velocity profile that I was given. So here, I'm solving for theta star. I'm solving for that term in the integral first. Then I'm solving for theta star by multiplying that term in the integral. So I kind of stretched that out maybe a bit too much. Then I'm solving for lambda. And once I have lambda, I can say, hey, lambda at negative 0.9 is going to be, yeah, all right. Negative 0.9 is going to be the separation point. And that separation point is going to equal negative 0.09. All I need to solve for, it's a 6th order equation, but it's really not that bad. The only term that's really difficult is the one in there, and I'm just going to raise that to the power 6 by inverting it. Once I invert it, I then have an expression, excuse me, 1 minus x separation over L, and that's 0.8777 and 0.123. Any other questions on this? Again, this is a reasonable question to ask on a homework. This is a reasonable question to ask you to think about. It probably is not something ideal on an exam. But The other thing too, and I kind of encourage you to try it, is to try and do these problems using things like Wolfram Alpha, which I find really useful in terms of solving complex equations and setting it up for you. And if you try it out, you can also get them to explain the solution. So you can work through it on your own that way. This is sort of the more complex part of chapter 7. So we've talked about pressure gradients. They drive boundary layer behavior. We have adverse pressure gradients, and adverse pressure gradients are the bane of all mechanical engineers. They slow flow near the wall. They create a separation point. They call it an S shape in the book. I would just call it a separation and potential separation. It's really a backward-facing S usually. Flow separation occurs at the point when wall shear stress is 0, leading to wakes and increasing drag. And you see this in a lot of different flow visualizations, and I probably will have a chance to show some of that in a few minutes. Favorable pressure gradients stabilize and thin the boundary layer, preventing separation. And Thwaites' method is really good for laminar boundary layers and predicting growth and separation. So continuing, you have other solutions. And I'm not going to go into the full sort of solution here. We're not going to rederive Gartler's solution. But he proposed an adverse gradient case, and it's this one, u naught over 1 plus x over L to a power n. And for this, for his case for laminar flow, n is equal to 1, and x separation over L is 0.159. And we start out with theta naught equal to 0. Momentum thickness is 0, which makes sense. And we're going to compare it to Thwaites' method. So again, Thwaites' method, lots to do. You have the first integral to solve. You have the combined equations to solve through. And then you make the lambda, substitute in the given profile, and you get theta squared equals 0.45 nu over u naught 1 plus x over L to the minus 1 to the 6th integral 0 to x u naught 1 plus x over L minus 1 5th dx. Theta star or squared equals 0.45 nu u naught 6 1 plus x over L minus 6 u naught to the 5th 0 to x 1 plus x over L minus 5 dx. Again, just substituting in terms, using the given velocity profile and using that as a basis to do the calculation. So all I'm doing is I'm substituting that velocity profile I got from Gartler for the u terms in the very top equation. Perform the integration. And you get L over 4 times the quantity 1 minus 1, the quantity 1 plus x over L to the minus 4. Substitute it back in. Compute the Thwaites parameter And you also have to calculate du dx. And you have everything you need. And again, out of all of the tools I've used online, I think Wolfram Alpha is absolutely amazing. So it's a for what it's worth kind of comment. If you substitute all of that back in, you'll end up with lambda, which is equal to 0.1125, 1 minus 1 plus x over L to the 4. It's not minus 4. And minus 0.009 equals this mess. And you end up with x over L of separation, which is 0.158, which is very close to what you got with Gortler's exact result. And again, I'm not deriving Gortler's result. I'm just presenting it as a result and as a solution. Any questions? Two more examples on this. One, I'm just going to look at airfoils. And you already know the answer to this question, but we go through it just to sort of convince you of that. Based on your understanding of boundary layers, which flow direction, left or right for the foil shape, will have the less total drag? And so a typical airfoil is going left to right. And here they're doing a reverse, and you have flow from right to left. And they're asking you to sort of define what happens in the two cases. If it's flow to the left, then in that case, it's coming from the tail all the way to the thickest part and then the leading edge. And the blunt end faces downstream, trailing edge. The flow sees a long run, a mild favorable gradient because it's expanding. And then it hits a short, steep gradient when it comes to the top, and then suddenly there's a huge separation. Severe separation, broad wake, high pressure drag. If you go the way we traditionally go, flow to the right, the blunt end faces upstream, leading edge. Stagnation point on the nose, flow accelerates around that airfoil. You have a mild adverse gradient as the foil tapers. It's sort of longish. And then the boundary layer can maintain itself over that short or over that distance. And then it sort of continues downstream. Less separation, long, narrow wake, lower pressure drop. Flow to the right has less total drag. And you see that, so and a shout out to myself on MC102. If you look at the airfoil, you can see why that is. You can see what the effect is as you go from left to right on the flow. You can see a rather controlled and small wake that results. And that small wake is what you're looking for. And that will probably be important towards the end of today's lecture when we talk about spheres. So consider the flat wall diffuser with constant width B. It's going in there. Show that the core velocity is approximately u0 1 plus 2x tan theta divided by w. Compute the wall angle for laminar separation at the exit using Thwaites method. So you have Qn equals Qx at whatever position. U0 An equals Ux Ax. An equals width times B. Ax equals width plus 2x Yeah. Tan theta times b, u naught w times b equals u x w plus 2x. I keep wanting to do that. B, and so ux equals u naught over 1 plus 2x tan theta over w. So that's my velocity profile. Velocity is going to change. I can use conservation of mass and confirm all of that, and I know that that's a good way to describe the geometry. All of that makes sense. The next step is really to sort of look at it with Thwaites method, which of course I have to use ux is equal to u naught 1 plus 2x tan theta over w. Ux equals u naught over 1 plus x over length effective, which is identical to the Gortler profile that we saw previously in 2 problems ago, 748. So in that case, 1 over L effective is equal to 2 tan theta, 2x tan theta. And at separation, it's going to equal 0.159. So here I'm not redderiving everything. Once I recognize that the velocity profile is the same, I can just sort of jump right ahead. So if we want it to occur at the exit plane, which is what we've tried for, and we have all of the information, length is equal to 2w, x separation is equal to L, we substitute all the terms in, we have 2w tan theta sep equals 0.159, 4 tan theta sep is equal to 0.15, and theta sep then is equal to 2.3 degrees. Just divide that 0.159 by 4, you have tan theta. So if you do that, you'll notice, or you would find from experience, that the laminar separation angle is much smaller than the turbulent diffuser limit. And again, this is one of the advantages to having turbulence. You sometimes want to have turbulence, even though it's more chaotic flow. What happens is that it helps stabilize things. And so you can have a much higher nozzle angle or exit angle for the diffuser in those cases if you have turbulent flow. Questions? So what we've done is sort of step out of the, or we've covered a lot on laminar boundary layers, and you have from laminar boundary layers a set of analytical expressions that are somewhat supported or buttressed, I guess is the way to put it, with experimental data. But then engineers don't care too much about laminar flow because laminar flow doesn't happen that often. And with flow separations, things get very difficult, and we need to go a little bit further. Boundary layer thickness or theory gives you a great qualitative grasp of flow behavior, but because of flow separation, it can't provide quantitative forces on an arbitrary body. And so this section of the chapter starts to present a lot of empirical data. And when I did this lecture yesterday, I was looking for a particular chart, and I realized White doesn't have it. So I then did an update to these notes, which you may or may not see today, but you definitely will see tomorrow. But drag of 2D, 3D bodies, blunt or streamlined, performance of lifting bodies, and it's how do you use this information, and how do we kind of go from sort of charts to data? So we have lots and lots of chart here. That's one of the things that comes out of this. Any body in a fluid stream will experience forces and moments about 3 coordinate axes. And I'm going to define x, z, y. So in the x direction, which is the streamwise direction, you have a drag force. In the y direction, you have a side force essentially pushing on the body. And z, you have a lift force. So it can be up or down, but it's a lift in all cases. In all of those cases, you have a corresponding moment. You have a yawing moment in the z direction, or about the z-axis, rolling moment about the x-axis, and a pitching moment about the y-axis. And if you kind of visualize this 3D object, you can see how those rotations occur. So you have pitching that occurs like this, rolling like this, and yaw like that. So force parallel to a free stream is drag, and that's what we're trying, generally we try to avoid. Force perpendicular to the free stream, it's useful and can support weight. That's why we fly planes. And then finally, side forces, it acts perpendicular to both drag and lift. For symmetric bodies aligned with the flow, side force and lift is equal to 0. And so, for example, if you look at any NACA 00 series airfoil, and there are a whole bunch of them out there. And in fact, one of the greatest things that was done was from the 1920s, the National Aeronautics Civil Administration, I got it, okay, did a whole bunch of wind tunnel tests. We use those wind tunnel tests and those tables to this day, despite the age, because we know a lot about them. Where we have problems right now is they did a lot of stuff at very high Reynolds number, above 1 million. Now we have a lot of small things flying, and we need to look at lower Reynolds numbers. Going back to chapter 5, you have C sub D, C sub L. Both of those are force dimensionless groups. And C sub D deals with drag, C sub L deals with lift. And when you deal with airfoils, you're going to see a lot of images or charts where you have lift over drag, or lift versus angle of attack, various other things, Reynolds numbers. You also are going to have the same for C sub D, but you also have CL over CD charts. In all of these cases, the tricky bit is to try and figure out what the frontal area is. So the characteristic area. So characteristic area for thick, stubby bodies, spheres and cars, are the frontal area. Planform area for wide, flat bodies where you're looking at the chord length, and that's how we define it in my work. And wetted area for surface ships. You have to deal with a lot of different types of forces on an object, but really what we look at are friction and pressure drag. So, for example, an airfoil is very well designed to deal with pressure drag. It minimizes the size of the wake. It allows you to fly with minimal problem. So friction drag is your problem. So when you design aircraft, you're designing for friction. And again, throwing back to what I do, I tend to look at ways of controlling friction drag. But you'll also notice that you have to be very careful in how things are defined. So one of these is based on planform area. One of them is based on frontal area. And you can see the curve behavior in these two cases is very different. And so if you try and sort of compare your measurements and you use frontal area here, you will get completely outlandish results relative to literature. So you have to be aware of where you're getting the data. And one of the things that's really important as you go through these charts is understanding how they get their data. There's a lot of data scatter no matter what you do. So the top graph is sort of an expression of that. You can see that as you kind of thicken this, you kind of deal with percentage of pressure drag. It's 100% pressure drag. as you go down. And at zero thickness, it's all friction drag. Zero thickness just means a thin airflow. So friction drag is drag due to shear stress, integrated over the body's surface, dominant for thin streamlined bodies. So the vast majority of aerodynamics, they deal with friction drag. Pressure drag due to pressure difference between high pressure front and low pressure rear, wake, dominant for thick, blunt bodies where flow separation is significant. And when you calculate C sub D, it's a combination of pressure and friction. So pressure drag is more important with cars. And you can, if you look in the text, they do show you some of the more remarkable vehicles that had very low C sub D. What's also interesting is how turbulence plays a role. Now, we've already seen that if you have turbulence, you often see a drop in your drag force. And there's a reason for that. C sub D for, say, a similar Reynolds number. So if I go and I look at this curve, and I look at the drag around us, yeah, it's a cylinder. I look at the drag around a cylinder. If I had inviscid flow, no viscosity at all, I'd have the dash line. The flow would go over and under and around this body very nicely. And if you can mimic that by having very low Reynolds numbers. So you can do, I think, up to a Reynolds number of 5, which is very hard to achieve. And that's one of the reasons why we might use glycerin to do some of these experiments. But your C sub D depends on where separation occurs. So for laminar flow, it's at 82 degrees. At turbulent flow, it's 120 degrees. And by changing that wake structure, by increasing or decreasing the wake width, you also decrease the pressure drag. Laminar separation is vulnerable to pressure gradients, separates early at 82 degrees, creates a wide wake and high drag, more resistant, much narrow wake, and much lower drag. This is why golf balls are dimpled, which leads into this discussion. And this graph, which is the graph I was looking for in white and I cannot find. So this graph is the effect of Reynolds number versus C sub D for a sphere. And the only difference is relative roughness. And so you can see that each of those lines corresponds to smooth for the solid line and then roughened for various types of spheres. The golf ball is right here. So you can see that there's a significant drop in the total C sub D for a particular Reynolds number. Smooth sphere, drag crisis, sharp drop in C sub D occurs at 4 times 10 to the 5th. And for a golf ball, which has 10 to the minus 3 for epsilon over D, so the roughness trips the boundary layer into turbulence much easier. Transition shifts left to Reynolds number of 4 times 10 to the 4th. I'm not a good golfer. I don't benefit very much from this, but good golfers do. And good golfers can hit really well because of the roughness. They get the distance out of the ball, not because they've hit it better. They've hit it better and they have the advantage of fluid mechanics. And that's a great place to stop, and we'll continue tomorrow.